Today's question sounds impossible. Can we actually compute arc cosine of I? On the real line, arc cosine behaves nicely, but only on a strict input range. Here's the real branch. The input x must stay between -1 and 1, and the output angle stays between 0 and pi. That yellow segment is the entire legal domain for the real inverse. Now look at our target. I is not a real number, and it's definitely not inside -1 to 1. So the real branch can't even start. If arc cosine of I exists, it has to live in the complex plane. So what is it? In this video, we'll show that arc cosine of I equals pi over 2 minus I times natural log of 1 plus square root of 2. Let's explore. To find arc cosine of I, we need a complex number z such that cosine of z equals I. So we start with cosine of z equals I and write z equals x plus iy. Think geometrically, w equals cosine of z maps the z-plane, input, to the w-plane, output. Expand cosine on a complex number, w equals u plus iv. Now watch a simple grid in the z-plane. Keep y constant. Horizontal lines map to closed oval curves in the w-plane, ellipses. Different y gives different ellipses. Keep x constant. Vertical lines map to open curves, hyperbolas. So the structure is clear, horizontal lines become ellipses and vertical lines become hyperbolas. Now we can finally target our goal. The point we want in the w-plane is w equals I. That's right here at 0 plus I. So the question becomes, which points z map exactly to that target? Let's explore the preimage of I. We scan across different x values in the z-plane, looking for where the mapping can land on u equals 0 and v equals 1 at the same time. The plots reveal a pattern. The candidates occur along vertical lines where x equals pi over 2 plus k pi. And once x is locked like that, we choose the correct height, y, positive or negative, so the mapped point lands exactly at w equals I. So we've located the solution set visually, special vertical lines for x and alternating y values that hit the target. That's the geometric fingerprint of the solutions. And in the next step, we'll convert this picture into the exact formula. Euler gives us the bridge here. On the complex plane, pick an angle x on the unit circle. The point at that angle is e to the ix. Its horizontal component is cosine of x, and its vertical component is sine of x. Reflect it across the real axis and you get the conjugate e to the minus ix. Same cosine, opposite sign. So e to the ix equals cosine of x plus I sine of x. E to the minus ix equals cosine of x minus I sine of x. Add them and the imaginary parts cancel, leaving a purely real sum. E to the ix plus e to the minus ix equals 2 cosine of x. So the identity we need is cosine of x equals 1/2 times e to the ix plus e to the minus ix. We're ready to turn the picture into algebra. Start from the identity, cosine x equals 1/2 times e to the ix plus e to the minus ix. Set cosine x equals I, and multiply by 2. E to the ix plus e to the minus ix equals 2i. Now clear the negative exponent by multiplying everything by e to the ix squared plus 1 equals 2i times e to the ix. Bring it all to one side and you get a hidden quadratic, e to the ix, squared minus 2i times e to the ix plus 1 equals 0. Let u equal e to the ix, then it becomes u squared minus 2iu plus 1 equals 0. Now use the quadratic formula. The solutions simplify to u equals I times 1 plus or minus square root of 2. And finally, we undo the substitution. E to the ix equals I times 1 plus or minus square root of 2. Next, we'll choose the correct branch to get the principal value of arc cosine of I. Euler turns our quadratic into an angle. We ended with e to the ix equals I times 1 plus or minus square root of 2. Now take the natural log of both sides. Ix equals ln of I times 1 plus or minus square root of 2. Split the log using the product rule. Ix equals ln of I plus ln of 1 plus or minus square root of 2. Here's where complex logs matter. Logarithm of I isn't a single value. It's I times pi over 2 plus 2 pi k. But for the principal value, we take logarithm of I equals I pi over 2. Now choose the plus sign, because 1 plus square root of 2 is positive and keeps the log real. So we get Ix equals I pi over 2 plus ln of 1 plus square root of 2. Finally divide by I. Since 1 over I equals minus I, the result becomes x equals pi over 2 minus I times ln of 1 plus square root of 2. That's the principal value, and it's exactly arc cosine of I. Thanks for watching.